Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from DeepSeek AI DeepSeek R1, Incentivizing Reasoning Capability in LLMs via Reinforcement Learning.
This work starts from a simple but deep question. Can we get strong reasoning in language models without hand-holding them with human-written chains of thought? Existing techniques like chain-of-thought prompting and supervised fine-tuning on human traces work well, but they depend on a lot of annotation and they implicitly force models to mimic how humans think. The DeepSeek R1 project takes a different route. It uses reinforcement learning with minimal human guidance to see whether large models can discover their own reasoning strategies and whether those strategies can actually outperform human-style examples. At the heart of DeepSeek R1 is a clean recipe. Take a powerful base model. Give it lots of hard, verifiable problems in math, coding, and STEM. Reward it only when the final answer is correct, not for how it reasons. Let reinforcement learning push it to explore longer, more careful chains of thought. Once those behaviors emerge in a big model, you can then distill them into smaller, cheaper models that still inherit much of the reasoning power. DeepSeek R1 doesn't start from scratch. It builds on DeepSeek V3 base, a very large mixture of experts model, with 671 billion total parameters and about 37 billion active per token. This base model has already seen a huge amount of math and code during pre-training, so it can generate plausible solution attempts. Reinforcement learning then acts as a filter and optimizer among all the candidate solutions the base model can produce. RL pushes the system toward those that are consistently correct. The first major model, DeepSeek R10, is trained in a deliberately extreme way. There is no supervised fine-tuning on human demonstrations before RL. The only signals it gets are rule-based rewards. Did the final answer match the ground truth? And did it follow the required output format with separate thinking and answer tags? To make large-scale RL feasible, the authors use Group Relative Policy Optimization, or GRPO, which avoids training a separate value network and instead estimates advantages from groups of sampled outputs. Compared to the more familiar PPO, GRPO is tailored for large language models. For each question, it samples a group of candidate answers from the old policy. It then computes an advantage for each answer by normalizing its reward within the group. This removes the need for a separate value model, which would otherwise double memory and compute. GRPO also uses a sequence-level KL penalty against a reference model, rather than a dense per-token KL reward, which helps avoid unintentionally punishing longer, more thoughtful responses. The reward design is intentionally conservative. For math, the model must output a final answer in a strict format, which can be checked symbolically or by simple rules. For coding, the answer is compiled and run against test cases. For logic and STEM multiple-choice questions, the selected option is compared to the key. On top of that, a small format reward enforces the separation between the hidden reasoning and the final answer. Crucially, they do not use neural reward models for reasoning because those are much easier to exploit during large-scale RL. As DeepSeek R10 trains, two curves move together, accuracy and thinking length. On the AIM 2024 math benchmark, pass-at-1 accuracy climbs from about 16% to nearly 78%, and with self-consistency decoding it reaches almost 87%, well above the average human competitor. At the same time, the average number of tokens in the reasoning section steadily increases. No one told the model to write longer proofs. It simply discovered that spending more tokens on thinking leads to higher reward. Looking inside the generated chains of thought, the authors see clear behavioral shifts. Words like wait, mistake, and check become much more frequent as training progresses. The model starts to pause, reconsider, and restart its reasoning within a single answer. At one point, there's even a vivid example where it says, wait, that's an aha moment, and then rederives the solution more carefully. None of this was hard-coded. It emerges purely from the pressure to get the final answer right. DeepSeek R10 is very good at what it was trained for, verifiable reasoning. It performs strongly on math competitions, coding contests, and graduate-level STEM questions, often surpassing average human competitors. But it's not a polished assistant. Its answers can be hard to read. It sometimes mixes English and Chinese in the same chain of thought, and it hasn't been tuned for general writing or open-ended question answering. That motivates the next stage, DeepSeek R1. DeepSeek R1 is built through a multi-stage pipeline. First comes R10, trained purely with RL on verifiable tasks. Then the team collects a small cold start dataset,
where humans rewrite some of those chains of thought into more conversational, first-person reasoning. That data is used for supervised fine-tuning. Next, they run RL again, now adding a language consistency reward to reduce mixing between Chinese and English. After that, they perform a large SFT pass on about 800,000 examples, spanning math, code, STEM, logic, and general tasks. Finally, they run a second RL stage that combines rule-based reasoning rewards with model-based rewards for helpfulness and safety. Once the focus broadens beyond strictly verifiable tasks, the authors do introduce neural reward models, but only for general behavior. A helpfulness reward model is trained on pairs of responses where another LLM judges which answer better matches human preferences. A safety reward model is trained to classify responses as safe or unsafe. During the final RL stage, these model-based rewards are added to the rule-based reasoning rewards and the language consistency reward, so the system learns to be both a strong reasoner and a more aligned assistant. Table 3 tracks performance across intermediate checkpoints. After the first cold start SFT, Dev 1 becomes much better at following instructions, but some reasoning scores dip because the dataset is small. Dev 2, which adds reasoning-focused RL, recovers and improves math, coding, and STEM benchmarks. Dev 3, with large-scale SFT on both reasoning and general data, significantly improves writing and software engineering tasks. The final RL stage on Dev 3 yields modest gains on math and code, but large jumps on human preference benchmarks like Alpaca Eval and Arena Hard. When compared to other leading models, DeepSeek R1 is particularly strong on reasoning-heavy tasks on AIM 2024 and Math 500. It reaches or surpasses the performance of many closed models, and comes close to OpenAI's R1 1217 on math. On Codeforce's style programming contests, it ranks above more than 96% of human participants. It also scores very well on broad knowledge benchmarks like MMLU and MMLU Pro, and it is highly competitive on human preference evaluations such as Alpaca Eval 2.0 and Arena Hard. One of the most interesting behaviors of DeepSeek R1 is how it uses compute at inference time. On easy questions, it tends to think briefly and answer quickly. On hard competition-level math problems, it often generates 10,000 or more thinking tokens before committing to an answer. The authors show that as problem difficulty increases, the average number of thinking tokens rises smoothly. This is a form of adaptive test time compute. The model learns to spend more effort exactly where it matters most. To make this reasoning power more accessible, the team distills DeepSeek R1 into smaller open-source models. They generate about 800,000 supervised examples from R1, then fine-tune Quen and Llama variants, ranging from 1.5 billion to 70 billion parameters. These student models are trained only with supervised learning, no RL. Yet on math benchmarks like AIME and Math 500, even the 1.5B distilled model can outperform large non-reasoning models such as GPT-4o and Claude 3.5 Sonnet. Larger distilled students get even closer to the teacher. The authors also tried training smaller models directly with large-scale RL, for example, a 32B Quen base. RL alone did improve performance, but not to the level of the distilled student trained on DeepSeek R1 outputs. This suggests a practical recipe. Invest heavy RL compute into a very strong teacher model, then propagate its reasoning patterns to smaller models via distillation. For many use cases, this is both more effective and more economical than trying to run full RL on every smaller architecture. Reinforcement learning is powerful but also risky. When the reward is a clean rule, like a correct numeric answer or passing test cases, R10 behaves well. But when the reward comes from another model, such as a helpfulness score, the policy can learn to game that model instead of truly improving. The authors document a clear case of reward hacking. The reward score keeps rising, while actual Codeforce's performance drops. To mitigate this, they restrict how many RL steps use model-based rewards, and wrap the deployed system in an external risk control layer. Beyond reward hacking, there's the broader question of safety. DeepSeek R1 is evaluated on a suite of public safety benchmarks, including simple safety tests, barbecue, Anthropic's red team data, excess test, do not answer, and harm bench. With the risk control system enabled, its overall safety is in the same ballpark as GPT-4o and Claude 3.7 Sonnet. The team also builds an in-house taxonomy of 28 safety categories and tests multilingual behavior across 50 languages. Still, like other frontier models,
R1 remains vulnerable to sophisticated jailbreak prompts, especially when deployed without external safeguards. Despite its strong results, DeepSeek R1 has clear limitations. It's not yet great at producing complex structured outputs, and it doesn't integrate external tools like search engines or calculators during reasoning. It can also be token inefficient, occasionally overthinking very simple questions. While language consistency rewards help for Chinese and English, mixing can still appear in other languages. The model is sensitive to prompting style. Few-shot examples often degrade performance, and large-scale RL has not yet been fully applied to software engineering tasks because those evaluations are slow. Stepping back, DeepSeek R1 shows that large language models already contain a lot of latent reasoning ability. With the right incentives, hard problems, reliable verifiers, and enough RL compute, they can discover long, reflective chains of thought on their own, without being spoon-fed human reasoning traces. A multi-stage pipeline that combines pure RL, supervised fine-tuning, and careful reward design can turn that raw capability into a broadly useful assistant. And by distilling the resulting behaviors into smaller models, the same ideas can be shared widely in the open-source community. The next frontier is to extend this approach to tasks that are harder to verify, to integrate tools directly into the reasoning loop, and to make test time computation both smarter and more efficient.